to have this possibility to deliver the opening lecture on this great symposium, World Congress. It's not only Copernicus anniversary, it's also my personal small jubilee. Exactly 50 years ago, that is to say, half of a century ago, I had the privilege to deliver the opening lecture during the Krakow part of the International Congress in 1973. The Krakow Congress was devoted to the investigation of the problem, the comparison of theoretical cosmological models with observational data. And I had a privilege to deliver the opening talk. Le temps passe vite, et nous vieillissons chaque jour. So we are now, today, 50 years after that event, and I have also another great privilege to address you today. Everybody knows that Copernicus stopped the sun and moved the earth. But only the better informed know that it was actually much more prosaic procedure. It was moving of the reference frame associated with the earth or that of the sun. The transformation from one reference frame to another reference frame is typically a relativistic procedure. In this sense, we can regard Copernicus as a predecessor of theory of relativity. And this moving of the reference frame from the Earth to the Sun was certainly a major achievement, but should we associate it with the theory of relativity and attribute to Copernicus what is the sole credit to Einstein? If one looks at the matter locally, that is to say from the perspective of what was happening in Copernicus's time, then indeed there is no basis for associating Copernicus' revolution with Einstein's revolution. In those days, if the notion of the system of reference was used at all, it was done so not explicitly and purely in an intuitive manner. Great scientific revolution, when regarded from a local perspective, never look like great scientific revolutions. So let's take a look from a non-local, from a global perspective. And this is how it looks like from the global perspective. The relativity idea developed through the ages, starting from ancient Greece, from Eratosthenes, who measured the diameter of the Earth, Aristotle, Euclid, and of course, Copernicus, and his successors, Kepler, Galileo, Newton, many, many other scientists, and finally, Albert Einstein. And this is this scientific revolution, the evolution of the idea of relativity through the ages, what I want to talk about. In other words, I will talk about the time-stretched theory of relativity. It was a long, long process, not yet completed. So let's take a look at the very concept of relativity. The general public absorbed something of Einstein, and this we can contemplate the results. Everything is relative, as we can read on this T-shirt. Everything is relative. It's attributed to Einstein. Everyone is relative, added Charles Darwin. Everything we hear is an opinion, not a fact. Everything we see is a perspective, not the truth. This is what our general public absorbed from the idea of relativity. But it is completely false. Let's take a look at the first ever relativistic revolution. In the dedication of his work, De Revolutionibus, to Pope Paul III, Copernicus quoted Lactantius, as he put it, a famous writer, but a lamentable mathematician. He quoted him as a warning to all those who, ignoring science, fight against well-established facts. Lactantius, an ancient Christian author, ridiculed the doctrine proclaiming that the earth is round like a ball, since in his view, this would presuppose the existence of people whose feet would be above their heads. This is how Lactantius thought about the impossibility of antipodes. All relativistic revolutions we will be talking about use essentially the same strategy. And it is not true that as a result of such a revolution, all relevant concepts become relative. Far from it. Only some non-essential concepts become relative, but precisely because of that, the other concepts reveal the invariant, that is to say, essential character. Let's take a look at this picture. The man who is standing at the North Pole of the Earth, and he's up and he's down. And indeed, if we look at the man who is on the South Pole, it seems that indeed his feet are above his head. But let's make a relativistic procedure. Let us switch the reference frame from one pole to another, from the North Pole to South Pole. Then something is changing together with the change of the reference frame. What was up and down on the North Pole will be down and up. It will be reversed on the North Pole. But not everything is changing. Something is invariant. Something remains the same. The invariant is this relativistic technical word for those magnitudes which do not change when we change the reference frame. What is here invariant? The center of the Earth. So this first relativistic revolution revealed an invariant, the center of the Earth. And if up and down is measured with respect to the center of this invariant, then there is nothing strange. Everything is correct. The people in Australia experience the same center of the Earth, and they don't fall from the Earth. In Aristotle's physics, an absolute reference frame was associated with the center of the Earth, because the center of the Earth was invariant, was something important. And the center of the Earth provided an absolute standard of rest. A body remains at rest with respect to the center of the Earth, and that body rests absolutely. Moreover, all bodies tend toward the center of the Earth, and this is their natural place, and this is natural motion which tends to the center of the Earth. And this idea was the basic idea of Aristotelian physics, which was obligatory to the modern times. Or indeed, till Copernicus. The discovery of the invariant character of the Earth's center was soon shrouded in the atmosphere of physical, astronomical, philosophical, and even theological interpretations, and developed into what we call geocentric model of the world. And over time, this model became a great obstacle to scientific progress. There is a saying, one of the poets said that every great idea begins like a heresy and ends as a superstition. And this is the popular view of the geocentric model of the world from the Middle Ages, but I want to say something rather extraordinary. I discovered that this model was in fact heliocentric, because let's take a look. In the center of the universe, we see the Earth. But in the center of the Earth is located hell. So in fact, it is a heliocentric model of the universe. This was a popular view on cosmology from the Middle Ages, and now we have a geocentrism as presented by astronomers. And you know, we know very well that it was Ptolemy who mathematically described the motion of planets around the Earth. The Earth was the center of the world. It was this fundamental invariant. And on this picture we see trajectories of planets with the Earth in the center, and they are computed with the help of modern computers. And we see that if we reaffirm the motion of planets with respect to the Earth, their trajectories, their paths, are extremely complicated. It's a very beautiful pattern, but very, very complicated. And Ptolemy was a great mathematician because he tried to simplify this complex net of paths and tried to describe them in mathematical model. And here in this corner, on the left side of the picture, we see the idea of Ptolemy. In the center is the Earth, in quote, in the center. Around this, the Earth, on the big circle called deferent, rolls another circle, and the planet is attached to the circumference of this little circle, which is called epicycle. And if these motions are added together, they give something approximate to the true path the planet describes in the Earth. But there is one very subtle problem here. We know today that planets do not rotate along the circles, but along the ellipses. And Ptolemy had to make a correction how to approximate the motion of planets on the circle when, in fact, it moves otherwise. And he put Earth not exactly in the center of the orbit, but you see this blue dot. It is a little to the left. And this was called equant. It must be added in order to approximate this pattern of circles upon circles to imitate ellipses. And Copernicus, what did Copernicus? He transferred the reference frame from the Earth to the Sun. But he also had to fight the problem of circular motions. And he preserved all this strategy of Ptolemy, with its epicycles, deference, equants, and so on. The only thing he did was to change the center from the Earth to the Sun. And this is why, mathematically, Copernicus had to, the same way like Ptolemy, exhibit a great genius to mathematically describe all these subtleties, all these discrepancies with what he could observe. And the man who put things in order was Kepler. The long-lived paradigm of circles. This paradigm originated in the ancient Greece. Plato, who said that the circle is the most perfect figure, shape, and this is why the planet must move along the circles. And it was Kepler who abolished that paradigm. Kepler had at his disposal very accurate observations of Mars, planet Mars. And he saw that the positions of Mars do not fit to Copernicus' model. And it took him a couple of years in order to convince himself that it is not the circle, but the ellipses. And when he did that, everything was put in order. So we see here on that picture, a picture to the left, it is one page from Copernicus, De Revolutionibus. You see here how he was fighting with the problem of circle. He draw here several circles, and you see that they give something similar to ellipses, but nevertheless he had to preserve these epicycles and deference and everything like that. The essence of Copernicus' revolution is that he moved the reference frame from the Earth to the Sun. It was a great achievement, and it is a very courageous achievement, because with that he violated Aristotelian dogma. The center of the Earth ceased to be the absolute standard of the rest. It is not only that he moved the Earth, but that he shook the entire edifice of Aristotelian science. And this fact initiated an avalanche of further transformations. In fact, it was not that important whether the center of the world was associated with the Earth or with the Sun. The next move would be to remove the center of the world entirely, to remove all privileged points from the universe. And Nicolaus of Cusa and Giordano Bruno and a few other thinkers preached that the universe had no center, or what comes to the same thing, that every point in the universe is its center. This was certainly an important achievement, but not a revolutionary step, because no essential invariant was associated with this procedure. No new invariant is associated with this procedure. Interesting things start to happen when we consider not stationary points, but when we consider reference frames moving one relative to another. And this was a turn to Galileo. The statement that all frames of reference moving uniformly to each other, relative to each other, are on an equal footing is known as the classical principle of relativity. Here on this picture, we see two reference frames. For the sake of simplicity, are aligned in such a way that the x prime axis is moving along the x axis of another reference frame. There are two inertial reference frames, and the primed reference frame is moving with respect to unprimed with the velocity v. The vector v is shown here. And the statement that all frames of reference moving in this way, or moving uniformly relative to each other, are on the equal footing, is the classical principle of relativity. And such reference frames, which behave like described a moment ago, are called inertial reference frames. And now we go to Newton. In Newton's theory, the standard of rest disappears. Previously, the standard of rest was associated with the center of the Earth, and now with Newton, it disappears entirely. Each inertial observer, that is to say, the observer associated with an inertial frame of reference, has his own private, so to speak, standard of motion. Space no longer looks like a rigid arena whose points remain stationary. Now the points are allowed to move uniformly and in straight lines relative to each other. And this was sanctioned by Newton's first law, which stated that a body on which no force is acting, or the acting forces are in equilibrium, is in a state of uniform and rectilinear motion. And this picture, there is illustrated a thought experiment invented by Galileo. In fact, not Newton, it was by Galileo, in fact, this law was known. Namely, let's look at that picture. The marble speeds up, rolling down along the ramp. And it accelerates because the ramp is inclined. And on the second part of the picture, in order to move the marble up, we must apply a force because it has to go up. And in the limiting case, when the ramp is flat, we are supposed not to apply any force, and the marble will roll uniformly without applying any force. So a body on which no force is acting is in a state of a uniform and rectilinear motion. And together with this first Newton's law, one could say the modern physics took off. In Newton's revolution, all inertial frames of reference, as we know already, are on an equal footing. But where are the new absolutes? Where are new invariant magnitudes? And until now, everything was more or less trivial. Now it takes a really unexpected meaning. Let's take a look at these two inertial reference frames. By the way, little clocks are associated with them, and we should observe that the same hour is shown on both these clocks. This means that in Newton's theory, time is absolute. It flows uniformly without respect of anything what happens in space and time. And what is invariant? When we change from one reference frame to another reference frame, we are looking for an invariant. And it turns out that laws of physics are invariant. This is a device to invent laws of physics. This is why I said that together with Newton's first law, modern physics started. At first glance, this seems totally surprising. How laws of physics could be deduced from simple changing reference frames. But after a moment of reflection, it turns out to be quite logical. We look at the world from a certain reference frame. When we move to another frame, our perspective changes, and the world looks different. However, if we carefully compare the pictures of the world obtained from the different perspective, and if we are rather clever observers, we can find that there are some elements that do not change when we change the reference frames. From the sea of details changing together with the change of reference frame, we extract a certain constant pattern which does not change when we change the perspective. Therefore, this pattern is not something subjective related to a particular point of view, but an objective property of the world, and nothing prevents us from calling it a set of laws of physics. And now, Newton's physics ruled the world through a couple of centuries, and now we are in the second half of the 19th century, and the new major discovery in physics was done by Clerk James Maxwell. He discovered the theory of electromagnetism. We have here his equations of the electromagnetic fields. Einstein was used to say that this set of equations was perhaps the most beautiful equations ever wrote in physics. And at the end of the 19th century, it turned out that some experiments were performed related to electromagnetic fields theoretically discovered by Maxwell. This experiment was related to the propagation of electromagnetic waves in space. I will not go into the details, but for me now it's important that these experiments were in conflict with the laws of physics known at the time. And this conflict looked at as a genuine crisis in the foundations of physics. After Newton, it seemed that physics was founded on a very solid basis. And now this basis was in danger. It was a long process, and this crisis was simply the most important problem in physics in the last decades of the 19th century, in the first decades of 20th century. And young Einstein in 1905 was the first to understand that what we need in order to settle this crisis was the new laws of transformation between the inertial frames. The inertial frames should be left in peace, but the laws how to transform from one inertial frame to another, these laws should be changed. Let's take a look at these pictures. We have again two inertial reference frames, and it was till now Galileo transformation which was needed in order to change from one to another. And now the Galileo transformation should be abandoned, and new transformations have to be used. They are called Lorentz transformation. And what is now the invariant, the new invariant? The new invariant is the velocity of light, which is constant, the same in all reference frames. This is one of the cornerstones of modern physics. Speed of light is absolute. It does not change with respect to Lorentz transformations. But there is a certain cost we have to pay. Let's take a look at these clocks here. They do not show the same hour. When we discovered that C is usually a letter which denotes the velocity of light. When C is constant, then it turns out the time must be relative. When we have a reference frame which is moving fast uniformly with respect to another, so the time goes slower in that same frame with respect to this similar clock associated with the other reference frame. If we look at these watches, so here is 4:00 p.m. and here 10 in the morning, so the time passes slower here. Of course, this effect is highly exaggerated, but nevertheless, the effect is real. So as soon as the speed of light became absolute, space and time had to become relative. Moreover, time, space, and the speed of light are no longer independent of each other, and their interconnectedness has made them one geometrical entity, which is called in modern physics space-time. Space and time are not separate, they are one geometrical continuum, or in more mathematical terms, manifold, and velocity of light is absolute. It does not change with respect to reference frames associated with the space-time. And this is the essence of the revolution in physics known as the special theory of relativity, which was done by Einstein in 1905. And now we could ask, what is the next step in the chain of relativistic revolutions? Einstein's brilliant idea was to reformulate the principle of relativity so that it could also be applied to the gravitational field. And the essence of the Einstein idea is captured by Einstein's thought experiment with a freely falling elevator. We have here freely falling elevator. The cable is broken down, and the elevator falls freely down. And what happens inside the elevator? Of course, this little poor man is falling with the same acceleration toward the Earth as all other objects. His head, his stick, they fall with the same acceleration. So this poor man will think that gravitational field is switched off, disappeared inside the elevator. And of course, vice versa. If we suddenly move the elevator up, then a new force will appear to this poor man, which will press all objects to the floor. So gravity can be eliminated or generated by choosing a frame of reference that moves with the appropriate acceleration, negative or positive. But there is one caveat. This is true, this is valid only locally, only inside the elevator, and only till the elevator reaches the ground. And this will be the fatal end of the experiment, of course. So we can eliminate or generate gravitational fields, but only locally. And to understand that it must be done locally took Einstein a couple of years. Of course, this was his intuitions, and always he tried to translate these intuitions into the strict language of mathematics. So although we can always eliminate or create a gravitational field locally, in order to keep the situation unchanged, because we eliminate gravitational field locally, so we change something, but the world should not be changed. The world is the world. So we should compensate for this effect. And mathematical considerations show that to compensate for a locally perturbed, introduced or eliminated gravitational fields, we must locally curve space-time. In other words, gravity manifests itself as a curvature of space-time. And these are outstanding Einstein's equations of a gravitational field, which described how gravitational field curves space-time. Now I should perhaps, as a not bad pedagogue, explain all these symbols Einstein used to write his equations, but of course I will not do that. But it reminds me of a story. In 1915, Einstein was looking for these equations, and he went to Göttingen and he delivered a series of talks about his hunting for the correct form of gravitational equation. And in Göttingen was David Hilbert, one of the greatest mathematicians of those times, and perhaps of all times. And it happened that Hilbert was attending Einstein lectures and was fascinated by the idea of looking for the correct form of the equations which would describe the gravitational field. And after that, Hilbert wrote a letter to his friend, and in his letter he wrote that This summer we had Einstein in Göttingen, and he delivered a very interesting series of lectures. From the physical point of view, they were extremely important and fascinating. But mathematically, as far as mathematics is concerned, every newsboy in Göttingen knows more about mathematics than Einstein. And now we are in Krakow, and I could say that we have no newsboys in Krakow, but perhaps news agents. Every news agent in Krakow perhaps understands perfectly well all these symbols, so I do not need to explain them. In today's fashionable lingo, modern physics has entered its post-relativistic phase. And it turns out that the new strategy, initiated by the general relativity theory, of compensating local modifications of a given physical field can be successfully extended to other fields than gravity. We are, of course, looking for some invariance, and the situation is connected with the concept of symmetry. In the situation where something remains the same, despite the changes of other things, we face a certain symmetry. For example, the reflection of my face in the mirror retains some essential features of the original, although its left side turns to the right and vice versa. So this is a problem of symmetry. Another very important notion of present theoretical physics. And the problem is that when we have something, what is called global symmetry, then this field which is subject to global symmetry cannot be measured, is not observable. For instance, if in this room everything suddenly becomes twice as big as now, nobody would notice any change. But if I myself become perhaps twice or 10 times bigger than now, then everybody would not notice that. The problem is that the global symmetry is not observable. But if we make a local perturbation, something small changes, all the rest is the same. This is local perturbation, it is observable, it can be measured. But it falsifies the reality. And in order to compensate, we must introduce a compensating field. These little arrows show this compensating field. And this compensating field is called in modern physics gauge field. So to make global symmetry observable, it must be locally broken, locally perturbed. But this must be compensated by the introduction of compensating field called the gauge field. And all modern theories in physics are in fact gauge theories. The main problem is to choose the correct symmetry. And then if we have this symmetry, we should perturb it. And then the mechanism goes very well. If we choose symmetries called local symmetry, Lorentz symmetries, we get general relativity theory. If we choose other symmetries, we get other gauge theories of modern physics. Here are a couple of examples. The so-called symmetry, abbreviated by the symbol U1, is the symmetry of electromagnetic force. Cu2 is the symmetry of the weak nuclear force. The symmetry U1 should be times Cartesian product with Cu2 is the symmetry of unified electromagnetic and weak force. And Cu5 is a candidate for the symmetries to unify the electro-weak and strong nuclear force. So if we choose a correct symmetry, if we guess the correct symmetry, then the gauge mechanism gives us a full theory. And now, the biggest problems of contemporary modern physics is that we know 4 different interactions or forces. Strong, here at the top of this diagram, electromagnetic, and weak, and also gravity. So there are 4: strong, electromagnetic, weak nuclear, and gravity. And let us look at the x-axis. This is energy. If the energy is 100 gigaelectronvolts, then electromagnetic force and weak force are unified because we guessed the symmetry and we computed the gauge theory, and we then checked that in CERN in experiments, and it has been verified. Then we would like to join to the electroweak force strong nuclear force, the so-called great unified theory. And we guess that the correct symmetry is SU5. But in order to verify that experimentally, we would have at our disposal 10 to 15 gigaelectronvolts, which is much more than we are able to obtain today. And if we had yet bigger energy at our disposal, 10 to 19 gigaelectronvolts, then we would have theory of everything, the big toe theory, theory of everything. So the problem is how to find the correct symmetry, and then it will be just a matter of a few technical steps. With this, will this be the successful end of the Copernican revolution, of Copernican theory of relativity? So it was a long process. Nicolaus Copernicus' theory of relativity, it started from ancient Greece, the first relativistic revolutions, and now the Hadron Collider at CERN, and our attempts to find the theory of everything. We have gone far beyond Copernicus, but we should remember that the measure of genius is the distance to which the effects of his achievements reach. Let's contemplate his face. Is he looking into a deep future, into the consequences of his revolution? Is he looking at great theory of everything, of which we had to dream our dreams only? Thank you.